Welcome to another data science deep dive on our technical track. The following presentation is by Vijay, Pappu, Senior Machine Learning Engineering Manager and Personalization Lead at Peloton. The talk focuses on any machine learning systems that rely on feedback loop or improvement. How do we measure the efficiency of a machine learning system? Improving machine learning models offline beyond the first A/B test can be achieved in several ways: feature engineering, complex models, larger data sets. He also shares that cohort analysis could potentially improve online metrics and much more. Enjoy the presentation.
Good morning, good afternoon, good evening to everyone joining this session. Hi, I'm Vijay. I'm a personalization lead at Peloton Interactive, right now the connected fitness company. And today I would like to discuss about improving the ML systems beyond the first A/B test. Please note that this talk is not related to any specific ML systems, like a recommendation engine or a machine translation engine, but more about focuses on any ML system that relies on a feedback loop for improvement. So with that, let's just dive in. Before we get started, I just wanted to give a brief intro into my background. I finished my bachelor's from India at IIT Madras, and I finished my PhD in machine learning from University of Florida. Since starting in the industry, I've been working on several consumer-related companies in finance, tech, music, and now connected fitness, where the common theme has been focusing on personalizing users' experiences. I've specifically been focused on like deploying and building ML systems that could personalize the user's experiences. So that is probably a good segue into what we are going to talk about today, is how do we measure the efficacy of an ML system. And probably most of you already know this. The efficacy of an ML system has always been determined using an A/B test. And the A/B test is considered as the gold standard right now in the industry, where in a typical setting, you are deploying a new ML model that's probably competing against a legacy system that's been built out of either simple rules or heuristics that you have. And what you would want to do is have this new ML system compete against the legacy system on some business metrics that you want to compare against. Typically, some of these business metrics could include, depending on the application-specific use cases, could be conversion rates, could be sales, could be increase in revenue, click-through rates, etc. Let's assume that you actually deployed your first ML system, which probably does better than your legacy system, because that's what you would expect an ML system to do. However, you would want to know how do we go about improving this ML system going forward, even though it has done pretty well in your first A/B test. So that brings us to the question of how you can actually go about improving our ML system beyond the first A/B test. Now, let's talk about improving these ML systems in an offline setting first. Because that's typically what is under your control, and there have been several ways that ML practitioners have typically done this in the industry. But you could broadly classify them as three big approaches of actually improving the ML systems. What you would expect to do is either you go about engineering new features that could provide additional information for improving an ML model. You could go about building complex models that learns nonlinear relationships among the data, or you could just take a simple model or a complex model and then train on bigger and bigger data sets. And typically, you would want to compare the performance of these new models on an offline metric, which is supposed to be in some cases an NDCG or a root mean square error or an area under the curve, predictive accuracy, etc. However, you would probably see an improvement in the performance of the models in an offline setting, but however, that does not guarantee that the deployed model would actually improve your online metrics as well. The online metrics that we actually discussed in the previous slide. What we really care about is improving those online metrics, and none of these offline techniques would guarantee that when such an improved ML model has been deployed would necessarily lead to an improvement in your business or an online metrics. So with that, probably the question now boils down to is how do you actually go about improving this ML system in a way that would allow us to actually see an improvement in the online metrics as well. Of course, there's no easy answer to this problem, but there have been several ways that people have tried in the past that could give us ways to actually be more targeted when we actually deploy these ML models. One such simple way, as you will see here, is called the cohort analysis. Probably you'll see this in literature in several ways, but the most simplest way to actually think about this is that when we actually run our first A/B test, you will actually see that the treatment, which is powered by an ML model, outperforms the control, which probably is powered by a legacy system. But typically, I think this is probably the most missed opportunity for the ML teams as to how you could leverage your first A/B test to further improve your ML systems. So I provide one example here where you could actually perform additional analysis at a cohort level or subgroup level that further deep dive into specific cohorts where the treatment is either underperforming or overperforming your control. Now, such cohorts, of course, are difficult to kind of just know. So most of them are typically powered by institutional knowledge or your intuition of how the models might work. So for example, in some settings, you might want to figure out the performance of the ML model against the treatment or against the control on, say, new users or specific markets. In some cases, probably you had new devices that you actually released into the market, or certain demographics that you want to check against if the ML model is actually doing better than the control. Now, of course, this is time consuming and it's expensive to actually think of different ways to actually slice and dice your data to figure out which cohorts the treatment is doing better than the control. So there has been some work that has been done in the causal literature that you could actually leverage here, where you could automatically determine some of these cohorts using a Kate estimator, where Kate is a conditional average treatment effect estimator, like the causal tree learning. I provide one example here from a book by Ken Aqua, where you can actually see on the right that there is an A/B test that was run for treatment versus control, and you will actually see that at the top level, probably across all cohorts, you actually see that the treatment underperforms the control. But as you dig deeper, you'll actually see cohorts where it is underperforming and cohorts that it's overperforming. Now, you could take this as an input to actually further focus your model improvements for the next iteration. So in this case, probably you would want to focus on the left side of this tree, where you will actually see that the treatment underperforms the control by 37%. So probably that's the highest area of improvement that you could focus on. And probably there are several ways to improve this cohort. One of the things that people would generally do is think of features that would probably capture this behavior better, include those features into the model, retrain the model, and then deploy a new model. Of course, this does not guarantee that you would actually improve your online metrics, but certainly something that would at least guide you in that direction, where you've actually taken inputs from your first A/B test and try to improve your next A/B test. Another way, probably I would say the more robust way of actually making sure that your online metrics are also improving with every model deployment that you do is through an offline-online evaluation framework. Before we dive into the offline-online evaluation, probably it's important to know what is an off-policy evaluation, which is closely tied into the offline-online evaluation framework. Now, when you're actually doing these offline experiments, what you would typically be doing is you would compare several policies with the production policy using an offline metric on evaluation data. And you would want to pick the best offline policy that does better than your production policy and probably go ahead and deploy that into production. Now, a policy here is a very generic term that is being used. In some cases, it could be as sophisticated as a new ML model trained by new features, or a complex model, or could be as simple as applying new heuristics to the current production model. So a policy could cover either of these spectrums. In the evaluation data is generally collected using a randomized policy, where a randomized policy means that a small subset of users are actually shown ML outputs generated at random rather than powered by any ML model. Now, of course, this is not always possible because this always leads to a degraded user experience, and people don't want to deploy or provide a bad user experience. So typically, collecting randomized data is sometimes not possible in some scenarios, or in some cases, it's pretty expensive to do. So in those cases, however, there has been some work on the causal inference literature that talks about applying the off-policy valuation just on observational data rather than basically collected at random experimental data using some counterfactual inference techniques. So there are still ways to actually use the current data that you're collecting and apply some counterfactual inference techniques to remove the bias and still apply the off-policy valuation and figure out the optimal policy. But still, of course, this does not take you a step closer to actually guaranteeing deploying ML models that would actually improve the online metrics. For that, what you would actually need to do is basically take a few steps further and eventually probably launch a few more A/B tests to understand the correlation between an offline metric and an online metric. So, for example, here is an example from the Netflix blog where you'll actually see that the offline metric and the online metric are basically powered by different models, and you can actually plot a simple correlation chart as shown here. However, this is powered after, say, a few A/B tests. So basically, in some scenarios, you will actually see that choosing the offline metric is also not trivial. Probably sometimes you might want to do root mean square error. In some cases, it could be precision. And in some cases, it could be area under the curve. Choosing the right offline metric that correlates well to your online metric is also an outcome of this offline-online comparison. So you would this process of running multiple A/B tests and making sure you have a good logging system that could capture the online metrics, which is, say, your conversion rates or the click-through rates, and compare that to the offline model that actually powered the test, and actually keeping track of their metrics as well. And then comparing both of them to see which one actually has the right correlation with your online metric. So having done all of that, you would probably end up with a chart that's kind of shown here. Now, how would you go about using this in future, right? So you could now continue doing your offline analysis or running offline experiments, trying out several ideas, and probably trying to figure out where on this line your offline metric would fall. That could lead you into what kind of online performance that you could expect by deploying such ML models. So an offline-online evaluation framework like this would allow you to actually predict ahead of time what gains you would see while deploying such ML models. Of course, running these A/B tests in sequence would take a long time, and it's also sometimes expensive. So what some ML practitioners do is actually launch multiple models as a part of one or a few A/B tests, so that they could capture these data points much faster, and that could allow them to actually now deploy more effective ML models into production. With that, I would like to basically, in conclusion, probably give you a few key takeaways as to how you can go about improving your ML models beyond your first A/B test. So in an offline setting, this is a standard problem. People have tried several approaches. to improve the models offline. I've kind of listed the most important ones here, say the feature engineering or the complex models, or even trying larger data sets with complex models. However, as we have seen, none of these can actually guarantee that when you deploy these models into production, they would give you a positive impact on the online or the business metrics that you actually care. So in order to make sure that you're deploying models that improve your business metrics, few things that you could do immediately are actually look at the results from your A/B test and do a cohort analysis using conditional average treatment estimators like causal tree learning can help you to identify those subgroups that could guide the improvements in the ML model development and potentially still guide you towards having an improved online metrics as well. In addition to that, of course, the long-term vision should be to actually have a robust offline-online evaluation that's combined with an off-policy evaluation framework that would tell you ahead of time what could be a potential improvement in your online metric when you deploy these improved ML models. So these two, one you could think of as a short-term solution to making sure you're deploying the right ML models, and one is probably a long-term solution in trying to figure out the right ML models to deploy. With that, thank you so much for listening, and I'm happy to take any questions that you have.
That was Vijay Pappu, Senior Machine Learning Engineering Manager and Personalization Lead at Peloton. Vijay shared how to measure the efficiency of machine learning systems and how to improve it beyond the first A/B test. If you enjoyed this presentation, if you'd like to watch more videos like this, you can subscribe to our DSS Insider program, where you can see our complete on-demand video repository from a wide range of topics on your own time. Subscribe in the link in the video description below, and make sure to follow us too. Thank you.